Life Sciences Week 2 Video Lecture 4, Atoms, Structure and Behavior. So let's take a look at our objectives today. We are going to describe the structure of an atom. We'll draw a diagram of the following atoms: hydrogen, helium, lithium, maybe we won't actually do all these, carbon, oxygen, nitrogen, neon, sodium, magnesium, calcium, iron. I bet we're not actually going to do all those, but we'll do quite a few of them. Define the terms atomic number, atomic mass, ion, cation, anion, molecule, compound, valence shell. Discuss what it means for an atom to be stable and the circumstances in which an atom is likely to enter into a chemical reaction. All right, so that's what we're up to today, which means what we're doing is making our giant step from physics to chemistry. So in chemistry, we're not quite as, let me say it like this. In physics, we are concerned about the movements of all things, great and small, from planets to molecules. In chemistry, we're really only concerned about the atoms and molecules, so it's the way small end of the scale of things. So we have a quote here by Marie Curie, which is, "Nothing in life is to be feared, it is to be understood. Now is the time to understand more so that we may fear less." So who is Marie Curie? Here she is. And why are we mentioning her? Because she was a pioneer in the field of chemistry, not just for her contributions to the field, which were numerous, and I'll touch on in just a second, but also because she's one of the very first well-known women of science of any field. So there she is, Marie Curie. So she worked with her husband, Pierre Curie, and they worked a lot with what is it called? Radium. Lots of things. They did lots of things, but they were the first to isolate radium. And so radon gas comes from radium. That's a radioactive material. And so from their work developed things like X-rays and using radiation they discovered that radiation kills cancer cells, things like that. So, however, and now Marie Curie lived, I actually don't know how long, but a good number of years. She lived, I want to say, into her 70s. And however, she died of aplastic anemia, which is a condition that comes from radiation exposure. So that's sort of the downside of being a pioneer, especially working with radiation. They had no idea at the time how deadly radiation could be and what they were working with and that kind of thing. So much so actually that their original notebooks that they used, all the time in the lab and kept all their notes in, are now considered too contaminated to touch safely. So through their lives, they were exposed to a lot of radiation and gave us lots of, very important contributions to chemistry and medicine. So chemistry, what is chemistry? Chemistry is the branch of science that deals with the identification of the substances of which matter is composed. So again, taking this step away from physics, we're looking at the movement of things, the movement of matter. How much force does it take to move something, and then how much will it take to stop the movement of something, and different forces and time and space and all of that kind of stuff. But here in chemistry, we want to know what are the substances that matter that physics is looking at is composed of. It is also the investigation of their properties, so the properties of these substances that matter is composed of, and the ways in which they interact, combine, and change, and the use of these processes to form new substances. So that will make more sense as we get into it. But basically what this means is that chemistry is the study of atoms. So we've decided that atoms are the things that matter is made up of, and I guess we should say something about that too. Well, let's take a look at our introduction in our notes. So in the mid-1700s, Newton was practicing alchemy. So remember when we talked about alchemy before, alchemy was the precursor to chemistry. So a lot of the things that alchemists were discovering, when we look back, we go, oh, well, those were actually the early discoveries of this new field, chemistry. So back in Newton's day, there were lots of elements that had been isolated and recognized. Mercury is one, gold is one. Gold, a lot of alchemists were trying to turn other things into gold. Carbon, they knew well what carbon was, and lead. And, interestingly, Newton used to play around with mercury quite a lot. Mercury is, what mercury is, right? It's the in the old school thermometers, it's that silvery liquid metal, and it's highly toxic, which is why we don't use it that much in things so much anymore. But he didn't know that it was toxic, and mercury is quite fun to play with because it's a metal that is liquid and rolls around and does kind of cool things. But when they in the 1970s, when some of Newton's like a trunk of his notebooks and stuff were I think they were up for auction or whatever. They were kind of rediscovered in the 1970s. When they went through that, they found some hair of Newton's, and they analyzed it and found it to be very high in mercury. So he exposed himself to a lot of mercury in his time. Okay, let's see here. So some of these some discoveries in the world of chemistry. J.J. Thomson in 1897 is the one who discovered electrons, and so that was our big step toward having the model of the atom that we still use today. Before that, what were some things that were happening in chemistry? We had Henry Cavendish in 1966 discovered oxygen. In that discovery of oxygen, he also was working a lot with oxygen and discovered a lot about the combustibility of oxygen, or the role of oxygen in combustion, I guess is a better way to say it. So we'll see that happening in the body actually when we look at that kind of stuff. When we look at redox reactions and metabolism and stuff. Oops, I said that wrong. Looks like Antoine Lavoisier in 1778 discovered oxygen. Hydrogen was what Henry Cavendish discovered. Sorry guys, I mixed them up. Anyway, we need to say a word about this before we dive too deeply into chemistry, that we know full well that quantum theory exists, right? All the stuff that we just looked at with all of our videos on physics. And so with quantum theory, we have a very different way of considering electrons and other subatomic particles than we do in relativistic mechanics. So remember, however, that relativistic mechanics holds up for us just fine in all of our day-to-day things. So things that are visible to the human eye, that are moving at observable speeds, relativistic mechanics tells the whole story and is a really useful tool. It's just that when we get into really small things, like atoms and subatomic particles, that quantum theory starts to be kind of an interesting thing, where we say, hey, these bits of matter, these things that originally we consider to be bits of matter, so the protons, the neutrons, the electrons that make up atoms, they're actually not so much bits of matter as bits of potential matter that exist as a wave until that potential collapses into form, into a physical bit of matter. So that being said, so that is all well and good and really interesting and stuff. However, in our initial look at chemistry here, we are actually going to go with more of a Newtonian model of the atom, and we're going to basically be working with the ideas of relativistic mechanics. When we look at the model of an atom, I don't know if let me see here. Oh, I did not include it in your slides, but it is in your notes. On the bottom of page 2, there is a diagram that depicts the difference between the two different theories of an atom. So that diagram on the bottom of page 2, on the right, what we see is an atom with all of its electrons being displayed as bits of matter, and on the left, what we see is an atom with its electrons being displayed as in wave form. So that's kind of, and looking at it sort of in a little more of a simplistic way is nice, early on when we're looking at this. It also is a little more of a two-dimensional look at atoms, which again is just sort of a convenient early way to look at them. But it's good to keep in mind that they're not remotely two-dimensional, and so they're very much three-dimensional. But and that they absolutely, exist. The electrons and other subatomic particles absolutely do exist in waveform until they collapse into particle form. So, just keep all that sort of in the back of your head while we're talking about this, because as we talk about it, we're going to pretend that every bit of atom is matter. So on we go. So on the notes now, I'm looking at page 3, and we're looking at atoms. And on the slides, what we're looking at here is a model of an atom. So this is the model. This is one depiction of the model of an atom that we're going to use. And so what we see here is atoms being made up of 3 subatomic particles. Protons and neutrons are the heftier of the two, so they're sizable. The neutrons are the heaviest, the biggest and heaviest of the 3 subatomic particles. Neutrons are found in the nucleus along with the protons, and so the red and the blue that you see in the middle there, they form the nucleus. The blue ones with the plus sign, those are protons. Protons have a positive charge. The red ones are neutrons, they're neutral, and so they have no charge. And the smaller green ones, they're not shown as much smaller here, but they really are much, much smaller, are electrons, and they have a negative charge. And so, that's our basic model, that we have protons and neutrons in the nucleus, in that center part, and then electrons orbiting around the nucleus. The electrons, let me think, what was I going to say about them? I don't know. I'll say it in a minute here as we move on through the notes. Okay, so let's define element and differentiate that from atom. So an element is a substance that cannot be split into simpler substances by ordinary means. What we're looking at here is the periodic table of elements. And so this table shows us most or all of the known naturally occurring elements. And some of these elements, though, might naturally occur only for a short period of time or whatever. And there are more that we can kind of create temporarily in the lab. But this is actually an awesome list of them. And so what do we have here? About 118 of them or so, which is a little different than 5-element theory that we look at in TCM. So wouldn't that be simpler if there were only 5 elements in Western medicine? There's not. There's 118, at least on this chart. So an element is a substance that cannot be split into a simpler substance by ordinary means. Okay? So what we're looking at on this chart, each of these squares represents an element. An atom is the smallest unit of matter that retains the properties and characteristics of an element. Okay, so each of these elements that's represented here has particular behaviors that it carries out. And we're going to take a look at where those behaviors come from. That's one of our main things we're looking at today. So any individual tiny speck of any of these elements that's hanging out all by itself there with its protons and its neutrons and its electrons, that's an atom. And atoms of, let's say, zinc or whatever, one of the elements that we could look at here, all of those atoms are going to have the same number of protons and more or less the same number of electrons. Let's say for simplicity's sake, in their natural form, and for the moment let's pretend they're always in their natural form, they're going to have the same number of protons as electrons. And then neutrons will vary a little bit, but often, most of the time, there's close to the same number of neutrons as protons, although that varies. Okay, so we have our 3 subatomic particles, and so the electrons, this is maybe what I was going to say, that the electrons orbit around the nucleus in what are called rings or shells. So what we can see here is the the two electrons that are closest to the nucleus, they are occupying a space. So that circle that you see there, that's their shell or their ring. That first shell, the one that's closest to the nucleus, for every single atom in the whole entire universe, has only 2 electrons has a maximum of 2 electrons in that first shell. The second shell, so once an atom, if we're looking at atoms that are bigger than that they have more than 2 electrons, then they're going to have more than 2 shells to house those electrons. So there can be up to 2 in the first ring, there can be up to 8 in the second ring. And so this one that we're looking at right here is a carbon atom, and a carbon atom has 6 electrons total, and so it has 2 in its first shell and it has 4 in its second shell. The second shell can hold up to 8. The third shell can also hold up to 8, and then from there we start to get bigger. So the third can also hold up. It's complicated. It will hold 8, and then we'll go up to 4 shells, and then we'll go back down to 3 shells for a bit until it gets up to 18. It's kind of a funny thing, but that really actually is no concern of ours today or ever, because those tend to be larger atoms that we don't have so much of in the body. We have some, though. Okay, anyway, so third and fourth rings can hold up to 18 electrons. So the first ring holds 2, second and third holds 8, third and fourth can hold up to 18. So that's why that's weird, why third is listed twice, because third holds up to 8, and then we add a fourth ring, but then some of those electrons from the fourth ring will go into the third, and the third then can hold up to 18. All right, things are strange on a small scale. The outer shell, or the outer ring, is always called the valence shell. So it doesn't matter how many shells there are. There could be 8 shells of electrons on an enormous atom. The outer shell is always called the valence shell. There could be 1 shell on a very tiny atom that only has 2 electrons. Its one shell its outer shell is the valence shell. There could be 3 shells, in which case the third one, the outer one, is the valence shell, okay? So the number of electrons in the valence shell dictates the behavior of an atom, okay? That is a key idea here. The number of electrons in the valence shell dictates the behavior of an atom. And I'll tell you why. The reason is that all atoms seek to have a full valence shell because they like to. There's a nice, warm, fuzzy feeling for atoms to have a full valence shell because they feel like they have everything they need. They don't have an interest in entering into chemical reactions. They are what is called stable when they have a full outer shell. So they don't need to interact, or they don't have a strong drive to interact with other atoms or exchange electrons or anything like that. So the number of electrons in the valence shell dictates the behavior of an atom as far as whether that atom is willing to enter into chemical reactions and what those reactions would look like. Because they will enter into chemical reactions to give up electrons or to gain electrons or to share electrons to form bonds. But they will do that so that, or until they have a full valence shell. All right, so atoms will enter into chemical reactions to attempt to have a full valence shell. That's in the notes. Sorry, it's not on the slides. So atoms can gain, lose, or share electrons to fill their valence shell. Okay, let's take a look at the periodic table. I actually got ahead in the slides there. Let's go back to the table. And let's kind of unpack this thing here. So any high school science room you've been in your lifetime, you've probably seen a big poster of the periodic table of elements up on the wall. And if you've had chemistry, then you probably know how the table works. And if you haven't had chemistry, we're going to go through and talk about how this table works. And even if you have had chemistry, Sometimes I feel like in a lot of classes, the how the table is organized part, I don't know, gets skipped. So many times I've had students that go, oh, so that's how it works. All right. So the periodic table of elements. So on this table, each square represents an element. I think I already said that. So in each square, we have a few things. Now this is actually kind of a simplified version of the table, which is nice because there aren't so many numbers here to look at. So what we see here, if we look at the top the top left square, we see a square that has a number 1 in its upper left-hand corner, and then it has an H in it, okay? So that H is the symbol for that element. So every element has a letter symbol, and it's either 1 or 2 letters. It's often the first 2 letters of its name, but not always, but sometimes it's the first 2 letters of its name in Latin, which is why if we look at the third one down, the third one below hydrogen. So hydrogen was our one in the top left. The one below that is lithium, and the one below that is sodium. So sodium, the symbol for sodium is Na, because in Latin sodium is natrium. So Na are the first 2 letters of natrium, the Latin word for sodium. Okay. What else do we have here? So each square represents an element. And the number that is in the top left corner of each square is that element's atomic number. So what is an atomic number? An atomic number, this is in your notes, an atomic number is the number of protons in the nucleus of that atom. So the thing that distinguishes hydrogen from helium, from boron, from carbon to nickel, from each of these from each other, is the number of protons in the nucleus. Okay, so for every single square on this table, there's a different number of protons in the nucleus. So hydrogen is the element that we get when there is 1 proton in the nucleus. Helium, which is way over on the other side, it's in white, it's in the top right-hand corner. Helium has 2 protons in its nucleus. How do we know that? Because we can see by looking at helium square. So helium, the symbol for it is He, so that's that one in the top right. Its atomic number is 2. So remember, the atomic number tells us the number of protons in the nucleus, so its nucleus has 2 protons. That's what we know by looking at this. So if we look at the next one, number 3, which is lithium, so lithium is the one right below hydrogen. So it's back over on the left side of the chart. It's the one right below the hydrogen, which was the first one we looked at. Lithium has an atomic number of 3, so there are 3 protons in its nucleus. Beryllium, the next one, number 4, has 4 protons in its nucleus. Boron, number 5, has 5 protons in its nucleus. The next 3 here in a row are all ones that are pretty common in the body. Carbon has 6 protons in its nucleus, or has an atomic number of 6. Nitrogen has an atomic number of 7, and oxygen has an atomic number of 8. So, so I could say to you, if you could find it on here, how many, or what is the atomic number of calcium? And if you knew that some charts have it all, they'll have the symbol, but they'll also have it written out in there too. But if you knew that the symbol for calcium was Ca, then you could find the Ca on there and go, oh, well, calcium's atomic number is 20. So I know then that calcium has 20 protons in its nucleus. Okay, so that is part of what defines each element and differentiates each element from the next is the number of protons in its nucleus, and the atomic number, the number on the top left, tells us that. Okay, there's more. That's the first part of understanding the table. The next part of understanding the table comes with the electrons. So remember how I said before that in their natural state, atoms have the same number of protons as electrons. So let's look at hydrogen again. Hydrogen has 1 proton in its nucleus, and so therefore in its natural state it has 1 electron orbiting around that 1 proton. Okay, so remember that protons have a positive charge, electrons have a negative charge. So in their natural state, those charges balance each other out. So So if we look across the chart at helium has 2 protons in its nucleus and 2 electrons orbiting around that nucleus that has 2 protons. So remember what we said about the shells. The first shell can hold up to 2 electrons. So hydrogen has 1 electron. Hydrogen has 1 shell, because it only has 1 electron. Helium still just has that 1 shell, and it has 2 electrons. But that first shell can only hold 2 electrons. That's the max that it can hold. So if we're going to look at an atom bigger than helium, so more with a larger atomic number than helium, we're going to need more shells to hold those electrons. So the next row down, if we look at lithium with an atomic number of 3, so it has 3 protons in its nucleus, is going to have how many electrons orbiting around it? Correct, 3. So those first 2 electrons are going to be in the first shell. But now we need a second shell for that third electron. Okay, so now for lithium we have 2 shells. And beryllium, right next to lithium, we have 4 protons in the nucleus. So we have 4 electrons orbiting around. So 2 electrons in that first shell and then 2 electrons in the second shell. And we could go all the way across that second row, and all of those elements in the second row all have 2 shells. So they have a full inner shell, and then each one in succession has 1 more electron in its outer shell to match its 1 more proton that it has in its inner shell. So if we look at that stretch of calcium, nitrogen, and oxygen, calcium has 6 protons in its nucleus, 6 electrons, so 2 in the first shell, 4 in its second shell. Nitrogen has 7 neutrons, and so it has 7 electrons, 2 in the first shell and 5 in the second shell. And oxygen has 8, it has an atomic number of 8, so 8 protons in the nucleus, 8 electrons, so 2 in the first shell and 6 in the second shell. And we can keep on going across there until we get to neon, which is 10, an atomic number of 10. And so neon has 10 protons in its nucleus, 10 electrons, which means that it has 1, 2 in the first shell, and then 8 in the second shell. And do you remember how many that second shell can hold? The second shell can hold 8 electrons. So now we've got a full second shell. So now if we look at an atom 1 step up bigger from neon, then we've got sodium. So back over to the left side of the chart, sodium has an atomic number of 11. Its symbol, remember, is Na. Its atomic number is 11, so it has 11 protons in its nucleus. It has 2 electrons in its first shell. It has a completely full second shell, so it has 8 electrons in the second shell, which gives us 10. But sodium has 11 electrons, so it has a third shell, and with just 1 electron in that third shell. So what does that mean? What's the pattern that we see here? We see that across the top row there are only 2 elements in that top row, hydrogen and helium. Those are the 2 elements that just have that first shell. In the second row we see 8 elements. Those 8 elements all have 2 shells. In the next row we have 8 elements also. Those 8 elements all have 3 shells. So as each step we take down the chart, we see more and more, or we see 1 more shell being added on. So for instance, potassium has an atomic number of 19. And so that is 1 more than 3 full shells, because the first shell holds 2, second shell holds 8, third shell holds 8, and then we have potassium with 1 more than that, and so it has a 4th shell. So the rows across, each of those rows, as we work down those rows, we're adding 1 more electron onto the atom. Okay. So each square, so the numbers in the top left are going to go up as we read the chart from left to right, and each of those then represents 1 more proton in the nucleus. But with that 1 more proton always means 1 more electron And so when we get to the point where we get a full valence shell, then we have to add on another electron. So part of what that means then, looking at the chart, is that all of the elements on the far right side, so that column where the squares are all white, so we have helium, we have neon, we have argon, we have, I think it's krypton or something. That sounds like Superman. I could be wrong. Xenon is the next one. Anyway, those are a special category of elements called the noble gases. The noble gases don't like to enter into chemical reactions. Why? Well, we can tell why by looking at the chart, because the noble gases all have a full outer shell. Every single one of them has a full outer shell, because they are all there on the right end of the chart. So like to go from argon, which is an atomic number of 18, to potassium that has an atomic number of 19, we have to add one more shell. So what else does that mean? That means everything in the far left column, starting with helium and then lithium and sodium and potassium and on down, those all only have one electron in their valence shell. If we go in one more from that, so starting with number 4 beryllium and down from that 12 magnesium and down from that 20 calcium and so on, those all have 2 electrons in their outer shell. Okay, and so in each of those rows, and you can see the numbers on the top of the row, that is, and so most of the time those numbers are going to correlate with how many well, not most of the time, but some of the times those numbers are going to correlate with how many electrons there are in the outer shell. So of course that's not going to hold true for like when we skip that whole like middle part that's kind of shorter than the rest of the chart. Anyway, but that's fine for our purposes. Okay, let's see. What else do we need to talk about with the chart? So each element from left to right has one more proton in its nucleus than the element to its left. Smallest is hydrogen. La-di-da. Let's see what else. Each row on the chart represents a shell of electrons. Every element is in its place according to size. So that is how the chart is set up. And then keep in mind that the number of electrons in an atom's outer shell determines its behavior. So it doesn't matter so much or very much at all how many atoms are how many shells it has or how many atoms are in the inner shells. It only matters how many atoms are in the outer shell. And that dictates an atom's behavior. In other words, that dictates the willingness that atom has to enter into chemical reactions. All right, moving on, we have a few more things to define here. Oh, look, here's something that we've already defined, which is atomic number. So atomic number we know is the number of protons in the nucleus of an atom. So if we look here at hydrogen, we know that hydrogen has an atomic number of 1, and we see that represented here with 1 proton in the middle. The mass number we haven't talked about yet, and we haven't talked about the atomic mass yet either, but let me just mention what we're looking at here is hydrogen that has 1 proton in its nucleus and 1 electron orbiting around it. Let's see if we can find one. Here's one, a good one to look at that has protons and, no wait, actually I want to find, this is a good one to look at that shows some of these other numbers. So here we're looking at lithium. So lithium has an atomic number of 3. So we already know what the atomic number is. What's the mass number? The mass number is the sum of the number of protons and neutrons in the nucleus of an atom. So, oh gosh. No. Here, let's look at helium. So what we're looking at here is helium, which has an atomic number of 2. So you can see those 2 protons there in its nucleus. It has 2 neutrons in its nucleus as well. So its nucleus is made up of 2 protons and 2 neutrons. So the mass number is the sum of the number of protons and the number of neutrons in the nucleus. So the mass number here would be 4, because there's 2 protons and there's 2 neutrons. Okay, so that's the mass number of this. So what we're looking at here would be called helium-4. And so that's the mass number of this particular helium atom. So atomic mass is the average mass of all the stable atoms of a given element. So that seems like a funny thing, and here's how that works. So remember that the behavior of an atom, it depends on the number of electrons in its outer shell, okay? And the number of electrons an atom has matches the number of protons that it has. Those things don't vary in the natural state of an element. Okay, so helium will always have 2 protons, it will always have 2 electrons in its natural state. What can change, or what is different from one atom of helium to another, is the number of neutrons. So that is not the same for every atom of helium in the world. So here we're looking at carbon, and we can see that carbon has 6 protons, and we already knew that looking at, well, down below it says it right there, but also if we looked at the chart we could find carbon and know that its atomic number is 6. And so it says right here that its atomic weight is 12. So its atomic weight is the same thing as the mass number. Those are 2 terms that mean the same thing. So the mass number, or the atomic weight, is 12. So that atomic weight or mass number is the number of protons and the number of neutrons added up. So we already know that the number of protons is 6, and if the atomic weight is 12, that means there are 6 neutrons here in this carbon atom. So we would call this carbon 12. So not every carbon atom has 12 neutrons. Some may have 13, some may even have 14. You maybe have heard of carbon 14 or carbon 13 or carbon 12. So that's what that means when we say things like carbon 12. We're talking about its atomic weight. So we're talking about an atom of carbon, and if it's carbon, it absolutely always 100% of the time has 6 protons in the nucleus. Otherwise it's not carbon. And if it's in its natural state, it has 6 electrons, and carbon usually is in its natural state. It usually does have 6 electrons. But from there, so now we can have some variation, and so we can have carbon with 5 or 6 or 7 or 8 neutrons. So that's what the atomic weight or the atomic number is. Now the atomic mass then is the average mass of all the stable atoms of a given element. So a lot of periodic tables will list the atomic mass, and when they do, it's listed underneath the symbol, and it will be listed out to a decimal, often at least 2 or 3 places, but often 4 or 5 places after the decimal point. And the chart that we have here doesn't have it, which is fine. But I wish I could think of any that I know in your notes. Let me look here. So do I have, no, I don't have atomic. I have some possibilities. Anyway, if you look at another, I think that the periodic table in the book does have the atomic mass on the chart. So you can look at that. And so, and that kind of tells you, let's say for carbon, let's say the atomic mass is 13.04 something. Okay, if it's 13.04 and carbon has 6 protons in its nucleus, which we know it does because that's its atomic number, but its atomic mass is 13 point something. That tells us that 13 is the average of all of the carbons that we can isolate, and we can weigh them and figure out how much they weigh, so then we can figure out how many neutrons they have. If 13 is the average, that tells us that some carbon atoms have 6 neutrons, some carbon atoms have 7 neutrons, some carbon atoms have 8 neutrons, and that exists in such a way that it averages out to 13 or whatever it is that carbon's atomic mass really is. But anyway, so it's an average of the mass of the stable elements of stable atoms of the given element. All right, what else? So when we say stable here, actually that means some isotopes. So an atom with a different number of neutrons, those are called different isotopes. And so some isotopes are not stable, and where they'll lose those protons really quickly and switch to a different isotope. And so if it loses neutrons really quickly, then it's not considered a stable isotope, and so it's not counted in the atomic mass. Okay, this is all so much more than we really need to be getting into, to tell you the truth. But anyway, that's what stable means here. But stable also can mean something else. So stable also means that when an atom has a full valence shell, therefore it isn't so terribly willing to enter into chemical reactions, it's also said to be stable. So the noble gases are stable. That means that they're not interested in gaining or losing electrons, so they're not interested in entering into chemical reactions, so they're said to be stable. Anyway, but when we're talking about atomic mass and we're talking about the stable atoms, we're talking about how stable is its number of neutrons. Okie dokie, let's move on. All right, so what do we know here? We know the number of electrons is the same as the number of protons. We know that atoms in their natural state have no overall charge, since the number of protons, which that's where the positive charge comes from, equals the number of electrons, that's where the negative charge comes from. So, and it doesn't matter how many neutrons it has, because they have no charge, they're neutral. But in their natural state, protons equal electrons, and so positive charge equals negative charge, therefore there is no charge at all to atoms when they're in their natural state. All right, and I already mentioned isotopes. Okay, let's look at different ways that we can draw atoms. And we already looked at some of these. And so there are different ways to draw atoms, and we'll just look at a few here. So here's hydrogen, and it's shown with that one proton in its nucleus. It's shown with one electron orbiting around it, and boom, there we go. We can count each of those, and it's pretty clear what we're looking at. Here's another way to depict hydrogen. So in this version, we have its symbol in the middle, and then we have the single ring that it has, and the one electron being shown in that ring. And up on top, on the left, we have its atomic number, and on the right, we have, on the left we have the atomic number, and then also the name of the element, and on the right we have its electron configuration. So in this case, it has one electron in one shell, so there's just that one, but we'll see some more like this where it's going to look a little different. Hydrogen, this is another way of showing hydrogen. So here they actually show the square from the periodic table. But then in the nucleus, what we see there is that P represents protons, so there's one proton. That N represents neutrons, there are no neutrons, and then we see the one electron orbiting around that one proton. So this is another way of depicting atoms. So here's helium, and so here with helium, we have everything all drawn out. We have the two protons drawn out, we have the two neutrons drawn out, and we have the single shell with the two electrons drawn there. So that's another way that we can represent an atom. So here's another version where we have the symbol. This is lithium, so we have the symbol Li in the center, and then we have the electrons all drawn out. So we have the first shell that has two electrons, we have the second shell that has one electron. Up across the top we have the atomic number, which is 3, we have the name lithium, and then we have the symbol on the right, which is Li. Down below we have the atomic mass, which is 6.94. So here's an atomic mass. Okay, so what does this tell us? This tells us that we know that lithium has 3 protons. And if we add, so then basically if we take 6.94 and we subtract 3, the 3 protons that we know are making up part of that atomic mass, if we subtract 3, we're left with 3.94. So the average number of neutrons that lithium has is 3.94, which is actually closer to 4 than it is to 3. So we know from that it's very common for lithium to have 4 neutrons. And then maybe even some lithium might have 5 neutrons, but some would have 3. Maybe some would have 2, but likely with this atomic number 6.94, we have kind of a mix of lithium with 3 neutrons and lithium with 4 neutrons, but it would be more common to find lithium with 4 neutrons since the atomic mass is closer to 7, which would equal 4 neutrons. The other thing we have here is the electron configuration. So here we can see how this electron configuration is shown when there's more than one ring. So we have 2, 1. So 2 in the first shell, and then in the second shell we have 1 electron. So that's lithium. So here's carbon. Carbon is something that we see so much of when we're looking at atoms in the body. So we have 6 protons in the nucleus. We're showing 6 neutrons in the nucleus as well, and then we're showing the 6 electrons. And so in this depiction, the protons have a plus sign, the electrons have a minus sign, and the neutrons have no sign. But we see the 2 electrons in the first shell, we see 4 electrons in the second shell. So down below, we see the atomic number is 6, and the atomic weight is 12, which tells us there are 6 neutrons in the nucleus. Here, this is nitrogen. So nitrogen has 1, 2, 3, 4, 5, 6, 7 neutrons, so 7 of those yellow balls with a plus sign on it in its center. And so then, and actually, look at how they show this. This is kind of weird, but they have 1, 2, 3, 4, 5, 6, 7 electrons showing around the outside. So they're not showing specific rings, which is kind of weird because personally I think it's nicer to see the rings because we want to know how many electrons are in that outer shell. But here, so once we get to the size of nitrogen or so, it begins to become a little unwieldy to show each of the individual protons and neutrons and electrons. So we can see, like with oxygen, which is bigger than nitrogen, this is kind of a cleaner way of depicting oxygen rather than drawing out 8 protons and 8 neutrons and 8 electrons. So what we have is the symbol O in the center that represents oxygen. We see the 2 electrons in the first ring. We see 3 electrons in the second ring. And that electron, wait, did I say 3? I meant 6 in the second ring. That electron configuration is up on the top right, so 2, 6, and that equals our 8, which is the atomic number of oxygen, which we see on the top left. So again, we see with a bigger atom, it's kind of nice to just sort of draw it out like this, where we see the atomic number in the top left, 11, and on the top right we see the electron configuration, so 2 in the first shell, 8 in the second shell, 1 in the third shell, and then it is drawn with the symbol showing all those electrons. Here's magnesium. So also has 3 rings, so it has 12, an atomic number of 12. Its electron configuration is 282, so we have 2 in the first shell, 8 in the second shell, so that second shell is all full, and then we have 1 more shell that just has 2 electrons in it. So that gives you an idea, and we can keep going. Here's potassium with 19 protons, and we're showing 20 neutrons. So if we added that up, we'd get 39. So the mass the mass number of this particular atom would be 39. And then we should find 19 electrons here. So first shell has 2, second shell has 8, third shell has 8, and then there's 1 more electron that we need to accommodate. So 1 more shell. So we have 4 shells for potassium. Only 1 electron in its outer shell. All right. So let's see. So in the case of like potassium or magnesium or sodium, where we only have 1 or 2 electrons in the outer shell, the easiest thing for those atoms to do, to have a full outer shell, remember, which is what they always want, is to have a full outer shell, the easiest thing for them to do is to lose an electron. So if sodium lost an electron, it would have 11 protons, because it always has to have 11 protons, otherwise it's not sodium. And rather than 11 electrons to balance that out, it would only have 10 electrons. So it would lose that last shell, lose that the 1 electron in it, but then it'd be like, hey, look at me, I've got a full valent shell. Let's go back to our chart here, our periodic table. So if sodium, find sodium on the chart. Sodium is atomic number 11. If it lost 1 electron, and so that it only had 10 electrons total, then it would kind of be walking around in the atomic world pretending that it's neon. So if we look at neon, which has an atomic number of 10, Neon has a full second shell. It's a noble gas. It doesn't like to enter into chemical reactions. It's happy like that. So sodium gets to pretend it's neon if it loses its outer shell. Like, if you're an atom and you're looking at an atom of sodium that has lost an electron, you can't really tell from a distance looking at it from the outside that it's not neon, because you can't really see inside to its nucleus. You can only see that outer shell. Atoms will do that. They will lose an electron or gain an electron to fill up their outer shell. The ones that are in the first two columns will tend to lose electrons, because the elements in the first two columns are the ones that either only have one or only have two electrons in their outer shell. The atoms that are in the green column, so that column right before the noble gases, those guys will tend to gain an electron, because they're just one electron away from having a full outer shell. And so they will tend to try to gain an electron to have a full outer shell. So when atoms do this, what they're doing is they're turning into something called an ion. So an ion is an atom that has gained or lost electrons, and therefore has an overall positive or negative charge. So if sodium loses its outer shell and loses that one electron, then it has 11 protons and only 10 electrons, so it has an overall positive charge of +1. If magnesium does the same thing, let me just flip through here. I think I have some diagrams of this. Okay, there's our definition. This is showing a hydrogen ion, but let me just finish with my thought about magnesium. If magnesium does the same thing, it would actually be inclined to lose 2 electrons, because it has 2 electrons in that outer shell. So it would have to lose 2 in order to have a full outer shell. So when it does that, then it has an overall charge of +2. And it's happy to do that, because then it has a full outer shell. It feels more stable that way. So it always will only have 12 protons, because otherwise it's not magnesium. But it's happy to lose 2 electrons and be magnesium with an overall positive charge. So it's happy to have 2 more protons than electrons. When atoms do that, they are becoming what are called ions. And let's look at this hydrogen ion. So what is this? So we know with hydrogen that it just has 1 proton, and it tends not to even have a neutron. So we can see here actually that the atomic mass is shown here, and is 1.01. So that's telling us that most hydrogen does not have a neutron. It just has that 1 proton. So it has its 1 proton. Its atomic number is 1. And so here we're showing this dotted line where the electron was, but it lost its electron. So now hydrogen has an overall positive charge of +1. So any atom that does that loses an electron and then has an overall positive charge, that is what we call a cation. So that's a particular type of ion that has an overall positive charge. That means it has more protons than electrons. That's a cation. So hydrogen actually can go either way, but here what we're looking at, and it's more common though for hydrogen to exist in its atomic form, in its ionic form as a cation. But with a hydrogen is kind of an interesting thing. When it turns into a cation, when it has an overall positive charge of +1 because it has lost its electron, what is hydrogen then? All hydrogen is, in its ionic form, is just a proton. So when we hear people talking about chemistry or talking about molecules or whatever, and we're talking about protons here and there and going wherever, a proton is a hydrogen ion. It's hydrogen that has lost its electron, and now all it has is that 1 proton that makes up its nucleus. So proton is a subatomic particle, but when you hear something referred to as a proton, that's synonymous with a hydrogen ion. When it's in its cation form, which is the more common way that hydrogen will take an ionic form. Okay, So one question is, why would we know, I already explained why an atom would do this, but the question, I guess, is how can it do it? How can it lose an electron or gain an electron? So first of all, let me define anion, so then we have both types of ions defined here. An anion is an ion that has gained one or more electrons, and so it has an overall negative charge. So an anion has gained an electron, so it has more negatively charged particles than positively charged particles, and so it has an overall negative charge. That's an anion. So cation has positive charge, anion has a negative charge. They're both types of ions, and so an ion is an atom when it's not in its natural state. The irony is that there are lots and lots of atoms, the ones that I pointed out, and the ones in the first two columns, and the ones in the column that are right before the noble gases. All of those prefer to be in their ionic state, because their ionic state, even though it's not the quote-unquote natural state where it has the same number of protons and neutrons, it's a more stable state for them because they have a full outer shell. Okay, so and one more word about ions before I say answer that question, how can atoms do this, is that it doesn't have to just be an atom that gains or loses an electron that can be in an ionic state. Molecules can be too. So we haven't defined molecule yet. We will in the next lecture. But I can just tell you already know, a molecule is two or more atoms bonded together. But in the next lecture, we're going to start to talk about bonds, about how atoms bond to each other to form molecules. So specifically, a molecule is two or more of the same atoms bonded together. That would be a molecule. So if we had a molecule of oxygen, that would be two oxygen atoms bound to each other. That's a molecule of oxygen. Very similar term is compound. A compound is when we have two or more atoms bonded together, but they're different atoms. So if we had, for instance, oxygen with two hydrogen atoms bound to it, we would have water, but water would be a compound. We'd still call it a molecule. We totally call anything that's two or more atoms bonded together a molecule, but if we say a molecule of oxygen, that means that the only thing there is oxygen. So the more accurate word for two or more atoms bound together when they are different types of atoms, or different elements, I should say, that term is compound. But we will actually get to that in the next lecture when we start to talk about bonds. So anyway, the point that I was making is that molecules can also gain or lose electrons and have an overall positive or an overall negative charge, and we'll see a little bit of that too. Okay, I wanted to flip through the last of these slides. So this shows sodium losing its single electron that it has in its outer shell and becoming a sodium ion. So sodium ion has an overall positive charge of +1. That's a common thing. Calcium will tend to lose 2 electrons because it only has 2 electrons in its outer shell. It's happy to lose them, and then it becomes a calcium ion. It has an overall charge of +2. And this is a chloride ion, so chloride goes the other way. So a chlorine atom has an electron configuration of 2, 8, 7. So 2 electrons in the first ring, 8 electrons in the second ring, 7 electrons in the third ring. That means it is 1 electron shy of having a full outer shell. And so if it picks up 1 more electron, then it has a full outer shell, and it has an overall negative charge of -1. So then we're going to call it a chloride ion. So it's a chlorine atom, and it becomes a chloride ion. So that's a bit about ions. And so remember that an ion will always have a charge to it, either a positive or a negative charge, depending on whether it has gained or lost electrons. But it will gain or lose electrons based on what its electron configuration is. So like sodium doesn't do so well gaining electrons. Now here's answering that question about how can an atom gain or lose electrons. So if we're talking about sodium, for instance, that just has 1 electron in its outer shell, that outer shell is actually, if we were to put it on a scale where we could see it, it is like thousands of miles away from the nucleus. And so the nucleus, so think of it in this way, that the nucleus has a gravitational pull to it. And the nucleus, the bigger the nucleus, the stronger its gravitational pull. So if the nucleus has 11 protons in it and 11 neutrons in it, that's a decent amount of pull. But if we only have one electron in the outer shell, that outer shell is like thousands of miles away from, it's not literally, but like, again, if we took it to a scale where we could see it, it would be, at least hundreds, if not thousands of miles away from that nucleus. So that nucleus doesn't have enough pull to hold that electron on very strongly, because that third shell is farther away from the other shells, or farther away from the nucleus is actually what I meant to say. But on the other end of the periodic table, if we're looking like at chloride, like we were just looking at here, chlorine can become a chloride ion by adding on one electron. Because that one more electron, like there are already 7 electrons in that shell, and so adding one more electron is not at all the same as like adding one more shell to hold one more electron, because it's still as close to the nucleus as those other 7 are. So there's a decent amount of pull, gravitational pull from that nucleus to hold that electron in place. So we'll see this kind of thing when we start looking at molecules, like for instance water. Water is made up of oxygen and hydrogen, and oxygen has a much larger nucleus than hydrogen does, right? So hydrogen only has a single proton in its nucleus, whereas oxygen has 8 protons and maybe 8 neutrons in its nucleus. So that creates a much stronger gravitational pull. So when oxygen and hydrogen get together and form water, the electrons that hydrogen is donating to that molecule will tend to want to hang out around oxygen more, because oxygen has a much stronger gravitational pull because it has a much bigger nucleus. So we'll see that in the next lecture. But all of this is just sort of teasers toward that. So let's see if we've covered our objectives for today. So describe the structure of an atom. Yes, I would say we've done that. Draw a diagram of the following atoms. I would say most of these we've drawn diagrams of, maybe not iron, which is the last one, but we certainly, I think you could at this point draw a diagram of iron. Define the terms. Did we do all these? Oh my gosh, look at this. I defined them all even though they weren't actually in the notes. So we talked about atomic number, which is the number of protons. In the nucleus, we talked about atomic mass, which is the protons and neutrons added up. We talked about ion, which is when an atom gains or loses electrons and then has an overall positive or negative charge. We talked about cations, which are ions with a positive charge. That means they've lost electrons. We've talked about anion, which is an ion with a negative charge. That means they've gained electrons. We defined molecule, which is 2 or more atoms bonded together, and compound, which is 2 or more atoms bonded together when they're different elements, and valence shell, which is the outer shell. And we know that that atoms like to have a full outer shell, and they'll do things so that they can get a full outer shell. So one thing that we've seen that they do is they form ions. So they gain or lose electrons so that they can fill up or empty a single shell, or gain electrons to fill up their outer shell so that they can feel nice and stable and not feel like they have to enter into chemical reactions. Here's one more teaser about ions with where we're going next. If something is an ion, it has an overall positive or negative charge, and something else that we've already seen is that is how charges feel about each other, right? So positive and negative charges are attracted to each other. Negative charges, 2 things with a negative charge repel each other, and 2 things with a positive charge repel each other. But if we have one thing with a positive charge, one thing with a negative charge, they will attract each other. So we'll look at that soon here too. And then our last objective was discuss what it means for an atom to be stable. So that means it has a full outer shell and it doesn't want to enter into chemical reactions. And the circumstances in which an atom is likely to enter into a chemical reaction. So we didn't quite get there all the way, actually, because we haven't talked all the way about chemical reactions, but that's coming next. But we know that an atom will enter into a chemical reaction to fill or to either fill its outer shell or to get its outer shell closer to full. Those are things that will inspire it to enter into a chemical reaction. But we'll define chemical reaction in the next lecture. So your homework for this section is to answer these things. One is, what are the 3 subatomic particles and where are each found? 2 is, what differentiates the atoms of one element from another? And 3, what drives the behavior of atoms? Okay, so answer those for me and email your answers to me, and then we're groovy. And then I'll see you in class next week. So I hope this was enjoyable. Have a lovely rest of your week, and I will see you soon.